Today we will implement the tries from scratch in Haskell. I assume that you know theory about tries, but what is a try? Actually, the try is a data structure which can be used to implement the storage of the set of strings. So we can insert a string into this data structure, we can search for a string, and we can delete a string. So it's somehow like a set. The traditional tries are used to store strings, but in this Haskell implementation I will use not just strings, so I can use I can change these strings to any type, which can be represented as a list, as a Haskell list of some values, which type has the implementation of equality type class. So all such types can be used for storing in our try. Also, tries can be used to implement some kind of HashMap, where the case must be strings or the list of any type which have equality type class, and as well as it can be any type. And we can implement this kind of HashMap to do fast searching of the values by their case. So let's go to our implementation. So what is the structure of the try? Of course we need to start from, but no, let's go with abstraction. Let's first implement the type class, which will provide to us the interface of try abstract data type. Okay, I will name it as try, and I put the C here from start as a class try. And what is our try? Our try has can be seen as some container type, and also it has some type of case, and each of these case is represented by type which can be seen as a list of some type k. Okay, and also this try has a value type. So actually here I write a multi-parameter type class. And now let's write type signature for this. At first, of course, we need to insert some elements into our try, and for this we will implement the insert function, which takes some elements which provide for us equality class, and we have this k represented as a list of these elements. Also, we provide it as a first argument. Also, we provide a value which we want to insert, and provide the container in which we want to insert our k value. Okay. And as a result, we of course produce a new container. Okay. The second function is search. This function also takes some equality k and the list of this case, and we have as a second argument provide our container, and as a result we can possibly provide the value. Of course, if this key in our container, then it has associated value, and we provide it when they do the search. And if we not find it, we provide nothing. So, and last function is a del function, which take some equality k, and also we need to provide a list of this case and the container, and at the end the built-in new container. Okay, this is the abstract definition of our try type class. The next thing we need to do, we need to provide some concrete data type which will implement this type class. And I will name this data type as try. It is a multi-parameter type constructor. It has two parameters, the k, the type of keys, and the value type. Okay, and how is it? What structure has it right? Okay, actually, this is it can be represented as a rows tree. It's like a binary tree, but the binary tree have in a node can possibly have maximum two subnodes, but rows tree can possibly have not only not only maximum two, but it has some set of subnodes, so it can possibly have infinitely many of them. Okay, and how we represent the rows tree? Of course, they can use the node constructor to construct some node. Which node consists from the k, from the value, look that this k is not a list of k, so it's just a k. It's just one char of our total key string. In the case of string, but here we much more abstract than just a string. We have a list of some keys, some chars. So, and we have a list, a list of subnodes, and this subnodes is. So we go to recursive definition here. It's a try itself. Okay, and let's drive show for this thing. Drive show because I want to print them. But as you know, the structure of the try, in the classic structure of the try, in the leaf nodes, they have values. So not all of the nodes will contain values, and that's why we need to provide the maybe here. And also there is some case then the when they have the root node. Okay, I can possibly make, I think, the empty constructor for this case, but I also can mark this case as a maybe k. So if I have in the node the k value, this means that this is a node. Actually, this is some char in our string, in the path of the string to the leaf from the root. This is some char. But if I have nothing here, this says to me that this is a root. Okay, so I just encode a root in this way. And also let's provide some simple function which creates to us the empty try. So we just create a node with a nothing, which says to us that this is a root, and of course nothing, root have no value, and we provide no list of subnodes as an empty list. And the next thing we need to do is to implement the first insert function. So actually this function will take the try and insert a string, or in our case any list of keys, this type which has equality key, into our container and produce a new container. So let's do the implementation. So of course I need to do the instance first for my withTry, some first instance, and this will be our try with k and with v. Okay, so we have these three types here, which are used in our function type signatures. And the first function is insert, as I said. Let's define it like this. We have keys and these and these, and we have equality for our keys, and we have this. They can provide some function from k to. We need to provide for this function k, v value, and then our try with k and v, and the construct a new try with k and v. So this is the type signature for our function. And let's do the implementation. So for save time, I will do this in the background and provide this function. Wait a moment. So I've done, and let's do some comments for this code. So we have this implementation for our function and for our insert function, and we have this helper function go here, which take a list of our which represent our list of keys. This list actually represents our key, or the string and the try, and we have this type t. This is our initial try, which we want to somehow modify its state. And what we do next? We call this helper. And in this helper, we can see that we can implement it via recursion. And the main things here is two cases. The first case, then when the pattern match some this list of keys and take some key, and when go to two cases, then our first key of the first char of the string is in our is represented into the subnodes, or if it's not represented in our subnodes. So if this first key is represented in the subnodes, we can go to the recursion. We can define our task in the terms of subtasks. So actually they need to so I mark this case that this boolean value is our element inside our sub-elements, subtrees. You can see this definition. This is we actually search here in our TS. The TS is the unpattern matched the list of subnodes here, and if any of our of these nodes contain, we can check the container of this first element, this predicate here, and if our element E, actually the first char, is presented into our subnodes, then they need somehow modify our tree our subnodes and provide a new subnodes. And how we do the modification? At first we delete our element. I use this function delete by, which takes some predicate, which takes two types of nodes. Actually, I don't need to provide the second type of node because I have it in outer namespace, and that's why I provide undefined here. Actually, it doesn't used because Haskell is lazy. I can do this, and here we do the checking of equality. If is our element is equal to k, then we delete it. So, and we have the new this field, this field, with where there is no this element, because it present there, and we put the new element again. So we put it again, but with our recursion, modified recursion definition. So we need to do the actual insertion, but the tail of this key, and we need also provide find node. So we need to find this node here and provide it into this definition, and it's built to us the new inserted subtree, which we modified here with the previous tree. So actually they do the insertion, the whole insertion in such a way. Okay, and the second case is what if our element not in the list, not in the list. In this case, the we can say that we doesn't need to do any modification of this subtree because it is not presented there, and all our tail path, actually all our k is injected in a tree like a path, so there is no any sub branch, and we use in this case to build this path using this definition, and we just add it to the subnodes. So we can say that there is no this node there, and we can just add it with all its subpath. And for this subpath, we just use this function builder, which just take the list of keys, so actually our string, and where recursion just build a node with this char, and where is no value. If we have tail, then there is no value. We mark this value. So if this is not the end of the string, so we mark this character that it is no value in our try. And also we, as a subnodes, provide a list of our path function applied to this tail. And the recursion, we build this path and inject it into all the try here. Okay. Actually, now I can try to compile this thing and do a little bit demonstration how it works. So I add this some pragmas and these imports, And let's try to compile this. Okay. Okay, it tells me that I need the implementations for search and del, and of course I need to provide them like a mocks in this moment. So what I need search function as undefined, and I need del function as undefined. Okay, we compiled. And now let's try to do some insertion. So what if I want to insert some string ABC into the empty try, the value 1, to the empty try. So we use this empty function. Okay, let's run, and you can see that I have this try. So they have this root node, and they have this A, and then they have this B as a parent, and then C. And they can see that parent has the value just 1. Of course, this is not very good representation, and in a moment I will implement some functions which will transfer this try into binary tree, into the rows tree. Actually, I have this import here. This is a data tree, this is a module which can have the good functions for printing rows tree, and I can transfer my try to this tree and print it, and this visualization will help me to demonstrate how this works. So what I want to implement? I want to implement the trans function, which what it's do? It's take my try of k and v and produce a tree of string, a rows tree of string. As I said, I can do this transfer, and of course for my try I need to have some equality type class constraints, and also I want my keys be showable and my with be the showable, because I want to transfer it into the string. I want to transfer each node to the string. Okay, how I do the transfer? So if I have the node, I can pattern match my key and the my try into I can pattern match it as a node which has k value and subnodes. And for this node, I want to transfer it into the node of the rows tree. And for element of the rows tree, I want to use the k and the value. And that's why I will take my pair of my k and value, and then I transfer it to my show, or with the show function, to the string, and I will use this value to my node, build a rows tree node. But also I have subtrees, and I need to provide them to my also for my rows tree. As we know, the list of our subtrees is represented as a list here. That's why the list is a functor, and that's why we can map it with our trans function again recursively, and this will transfer any of these tries of the list of tries into the list of trees. So, and this is correct argument for our construction. Okay, let's define it like this, I think. And after I do this translation, I can define the print function, which takes some try. And what it's do, it's at first transfer this try into the rows tree. Then after this transfer, I want to draw this tree. This module of the rows tree has this function. And after I the draw tree transfer it to the string, and then I need to put this string with the new lines into my screen. Okay, and actually this is the definition of my function. And next thing I want to do, so let's check that it works. Let's create some try and print it. Print this try. So let's save it and print it. And you can see I print this try. So we have empty string as a root. We have then A, B, and C. So actually this is the visualization of our try. And I can go to do some more helpers. The second helper which I want to do is the from list function, which will take the list of pairs which contains my keys and values. And from this list of pairs I want to build a try for these keys and values. Okay, and of course I need to provide equality constraint. Okay, and this is easy because I can take my list of these pairs and use fold R function. For this function I need to provide the first function which takes a pair. Of course I can pattern match this pair with K and D, and it takes some try as a second argument. And what I do, I just do the insertion of this K and D into my try. Okay, so this function will construct to me the whole try from these pairs. Of course I need to provide the withTries initial argument for my folder, and I need to provide the list itself, which from which I want to do the construction. And let's create some try here. I will use my helper function, and the next thing I need to provide the pairs. Of course the pairs is the my keys and my values. Okay, what if I want to insert such things into my try? Actually what we do here, we have the HashMap based on this try. Okay, but also this HashMap you can use as a set container, because they have we can view at our case as our set elements. Okay, let's recompile. What I have here, I have here some problem in the syntax. Of course I forgot this type signature here. And the done. And let's print our try these three strings. And you can see we have this try representation. We have this root with empty string, and then we have A, B, C, D, A, Y, Z, A, Y, Z, and they have A, K, G, J, H. So as I do here, but here they have in the structure of the try. Okay, and now we need to implement the last two functions, the search function and the delete function. Let's start from the search function. I think it will be more simple. I will do this in the moment, and we will review this. So how this is the implementation. How we do searching? Actually, the searching, they can see that it can be done in recursion here, and what they do, we take pattern match our searchable string, and they check that this is element in our subnodes. So if it is in subnodes, then they can recursively just continue our searching. But otherwise, they can say that they not find this, and they say this. So, and in the base case, when they have go through all of our case, list of case, and they have empty key, and in this case, that means that they stop at some point, and at this point they have we have no one of nothings, and that's why all of this case of the string inside our try, and they say that we need to just pattern match this try and extract the value and return this value. Actually, this thing will just search for a value inside our try. Let's check this. For example, what if I want to use my try z to search for a k? What if I want to search for this key in my try? And you can see that it's fine to me just 3 because it is in our try. But what if I want to find kg? You can see this is nothing because there is no value associated with the string in our try. Actually, there is no string in the kj in our try. Of course, any other thing will give me nothing because there is no values. So actually, this is act like a hash map. Okay, and let's go to the last function, the delete function. So here they have the delete implementation, and how it works. The main idea is to use this helper function go. So actually they can do our deletion, the recursion also, but we need to provide some extra information. So at each step we can say that they can so as always I do a pattern matching here of my key string, and at that step I can say that I can delete this node E. Of course I can delete it if it inside the subtrees, and it can be deleted. What I mean it can be deleted, I can delete it if it has no sub it have no neighbors. So and also they deleted the subnode. So I delete the subnode, the recursion, and if this subnode can be deleted, so, I mean structure can in the structure, I can also delete this node, but only if there is no other subpaths from this node, and I check this by this length of my find node subnodes. If it has some subnodes, I need to freeze this node in the structure because from it go other parts into our strings. So if there is emptiness here, then it can be structurally removed. And I check this logic. Okay, and we do these two cases. So if we can delete it, we catch this boolean value when the transfer our sub nodes listed like this, and actually they just delete this node from this sub nodes. But otherwise, if they can delete it, we just modified all the sub node tree, and this done by this. So at first we delete it, and at the second they add it again but modified. And how we modified it? Of course we modified it with recursion. And also with recursion they get this information about that the next node deleted or not. So it used here in this predicate, and they check this. If the next node deleted and our current node is empty, then they also get deleted. And this kind of recursion provides to us the whole logic, and let's check that this thing is work. Okay, let's I will write the go function type signature here to help understand what happens. So we take a list of case, and we have some try which we want to delete this, and we provide actually here the pair, our deleted try actually. And the second thing is the information is we do any deletion or not. Okay, so if our further we do the deletion of further nodes, we can in the case of emptiness delete our current node. Okay, let's reload. I do some error. So I think I need to write up signature here. And let's delete. So we have this try, and what if I want to delete from this try, for example, a, y, z? Okay. So I want to delete a, y, z from this try z, and I want to print the result. And you can see that if I delete this, I just have these two strings here. But let's try to, for example, remove k, j, h. Okay, you can see it deleted. Also, I can remove a, b, c, d, and it also deleted. But what if I want to remove something that is not in our list? You can see that I have this exception because at some line, I think 67. So because I can't find this element. So okay, for simplicity, I will stay it as it is, because I assume that k in my try. Of course, you can easily change this by adding some guards here. For example, we can search it first. I can search for a key here, and if the result is nothing, I can say that I can define it as a try itself or throw some error, but I will state this as it is because I do the main thing. I implement the logic of the tries. So actually they do the insertion, they do the searching, and they do the deletion. And actually they have the pretty fast hash map. And also we have a try. So guys, thanks for watching. Push like, push subscribe, write comments, and see you in the next video. Bye bye.